Welcome to another video for AQA AS Chemistry, and today I'll be doing a video on introduction into alkenes and their reactions. So first of all, what are alkenes? Alkenes are hydrocarbons, but they have the functional group, at least one carbon-carbon double bond in their structure. It could be one or one plus, pretty much. So if there's a structure with a hydrocarbon, which you already know before, is a compound of only hydrogen and carbon, but one of the carbon groups is C a carbon-carbon double bond. If there's one of those or more than one, it's an alkene. They are unsaturated, so alkenes are unsaturated because of the carbon-carbon double bonds, meaning that an alkene contains two fewer hydrogen atoms than the alkane with the same number of carbon atoms. So an ethane has 6 hydrogen atoms, but ethene would have 4. The formula is usually given by the homologous series, and the homologous series is just a series of compounds with the same general formula. For an alkene, it's CnH2n. That's the general formula for alkenes. As you know, for alkanes, it's CnH2n plus 2, which is different. So, and that's 2n is just to represent the fact that it is unsaturated, which in this case, a saturated compound for hydrocarbons would mean every carbon has the maximum number of hydrogen atoms that it could possibly have, whereas unsaturated means it wouldn't have the maximum number of hydrogen atoms that it could possibly have. Now we're talking about how reactive they are. Alkenes, although they have high bond enthalpies, potential, which is just the potential energy stored within the bond, in this case, a double bond, they're more reactive than alkanes. This is due to the double bond. This is due to the double bond having a high electron density. Which probably is kind of a typo there, but they're stronger. There's a double bond, so it's a stronger bond. But because there's a high electron density in that region of the double bond, that means that they're very reactive and they can act as a nucleophile. So if I just show you this compound here. Yeah, let's draw it out. So let's say an alkene, as an ethene, it's the simplest alkene you could probably have. But I'm gonna draw it out in terms of what it represents in the double ones. So I'm not gonna do the displayed formula. So you have your carbon-carbon bond here, and then you have, this is the sigma bond. This is what we call, you don't need to know these types of bonds specifically, sigma and delta, and so sigma and pi bonds, but kind of knowing of them is useful. Simple sigma bond, your pi bonds. You will learn more about these as you go, but this is just to give you a general overview of why they are like this. These pi bonds are equally repelling each other, so these are just representing electron clouds. Electron clouds are just an area where the electrons are most likely to be. So they're most likely to be in this region, and they would equally repel these bonding pairs equally as well. So there's 4 of them in total. So this pi bond here equally repels this one, and likewise here. So the alkenes have a carbon-carbon double bond, meaning that they have one sigma bond and also, one pi bond. So these are the pi bonds that are represented here, above and below the plane. So they oscillate above and below the plane, realistically. That's what's represented there. And obviously the 4 hydrogens as well. Forgot to represent them here. These kind of like, these pi bonds these electrons here overlap. They overlap above and below the plane of the carbon-carbon sigma bond. The bonding in alkanes only consists of a single. So in an alkane, you've only got this sigma bond, whereas in alkenes you have a sigma bond and a pi bond. Meaning that so because in alkanes you only have a single bond, a sigma bond, it means that that's what allows the alkanes to kind of twist and it can change the structure a bit. Like it's not as rigid, so it can be twisted around. Whereas in alkenes, the pi bond along with the sigma bond in alkenes prevents the rotation. So that's why carbon-carbon bonds are generally regarded as rigid, and they don't bend or can't be twisted around or manipulated in any sort of way. So the shortest alkenes or alkenes in order, the ones you generally see are ethene, propane, butene, and pentane, and these are the given formulas here. But if you, as long as you remember the general formula, CN, the homologous formula for alkenes, CnH2n, they all follow it. It's just that hydrogens have double the amount of, there's double the amount of hydrogens compared to carbon atoms. That's all it is. Very easy to know. You probably don't know that from GCSE. Now for the reaction of alkenes. Alkenes are molecules with a double covalent bond, and there's a high electron density between the carbon atoms because it's a double bond. The reaction of alkenes is generally like, so alkenes react with several reagents in addition reactions, and the alkenes are nucleophiles because of the high electron density between the carbon atoms. So because of this kind of because it's so electron dense here, it can actually means that the alkenes act as the nucleophiles and more than the other compounds. So you have actual electrophiles that are reacting with the nucleophiles, and they usually, generally when we're talking about alkenes reacting, it's electrophilic addition, because an electrophile is being added. There's no substitutions or eliminations. It's just an electrophile being added, and I'll show you one example here. I'll just draw you an example with hydrobromic acid, or hydrogen bromide as it's generally given. So here's one mechanism. And then go for this here. Negative. Always write your partial charges. And it'll go from, it's always from the negative charge to the positive charge. So always your delta partial negative, your delta negative, delta positive. Always going from, let's probably do it like this here. So with that gets, that's probably a little. Good. Yes. So that's your, without, so the electrophile is being attracted by the nucleophile, and it's breaking this carbon-carbon double bond here. When it happens here, this obviously is not gonna, this hydrogen only forms one bond, so this bond would actually break. It's not gonna, the hydrogen isn't gonna be gained there, so it's gonna do that. When that happens, that gets released. So then now you have, this is a symmetrical, ethene is a symmetrical molecule, so it doesn't really matter either way you do. It's the same thing really. You'll get a compound like this. Can I write that? Or... Here we go, yeah. So that H has been, that hydrogen's added there. And then we have a carbocation here. And then this, I usually put a circle around my carbocations just to represent. Now this nucleophile is being attracted to here for nucleophilic addition, but it's generally, the whole mechanism is an electrophile in total being added. Yeah, here you go. And now you have your final product. And now you have your final product. I should point out that these are actually reversible reactions, so that's my bad for not representing it as so. These are actually reversible reactions. Ooh. And then this is your compound that's getting formed. I should probably change it, to be honest, to something else, because this is really not working with me right now. I shouldn't have used the sketch. You should have used... I shouldn't have used diagram. But we learn. So, electrophilic addition. The mechanism above is called electrophilic addition. You know, it's actually really annoyed me, to be fair. Yes. Yes. All right. The mechanism above is called electrophilic addition because an electrophile is being added. They all react in a similar way with sulfuric acid and bromine water. The reaction I've shown, the scenario that I've shown you above is between hydrogen bromide and ethene. So I can show you another reaction below. So it's not exactly the same, but the same principle as the reaction I've seen above. So let's do this here. So so another ethene molecule. These are generally regarded as dehydration reactions. I'm going to show you why. So you have your sulfuric acid. It actually acts as a catalyst for this reaction, actually. So it's not as straightforward. Partially positive as usual, partially negative. I just realized you guys can't really see what I'm doing from that angle. I'll probably do it like that, there. When that happens, again, ethene is an asymmetric compound, so it doesn't really matter which side that you, it doesn't matter which side you do your carbocation on, so long. Oh, actually, I haven't even done a proper carbocation actually. Let me just do that part again. I'll do that part again. Yes. Carbocation here. I'm not talking enough, am I? I just realized I'm like getting way too into this. But yeah, it's just a simple reaction of like the same kind of principle as before, really. You're going for your negative bond, from the nucleophile to the electrophile. That bond will break because obviously hydrogen only forms one bond. And now you're left with this nucleophile here. And that kind of does a bit of nucleophilic addition here, but it's an electrophilic addition. The names of all these compounds, the names of all these mechanisms, like a nucleophilic addition, electrophilic addition, they're always self-explanatory. So if you ever like to say, what is nucleophilic addition? So always nucleophilic addition elimination. It's just a nucleophile being added and being eliminating another nucleophile. Like that's just all it is. So like if it's an electrophilic addition, electrophile is literally just being added, and the rest of this is all part of the original electrophile, which is being added to the compound. So that's all it is. So now there's another reaction with these. The reason I call this is regarded as a condensation. dehydration reactions, because you can actually convert it in a condensation reaction to form water. So to form an alcohol, in this case ethanol, which is used in wine or in most alcoholic beverages. You don't actually need to know too much in detail from this, but you just need to know it can undergo a condensation reaction. Yes. So this is a condensation a condensation reaction, or a dehydration reaction, this is generally referred to, and is so this right here during that process is condensation, and that forms water, really. So water is being formed from this reaction. It's removing water technically from this reaction. So you can have the same reaction with bromine. I'm just going to keep giving these examples because these are the main three that come up in the exam. And the reaction can also be done with bromine or Br2. The partial charges are assigned to the bromine atom because of the high electron density of the double bond. The double bond repels the bonding pair of electrons and polarizes the bond, as shown in the mechanism below. So this part here about polarizing, it's just that it's literally this part here. The partial charge is just due to the fact that you have this very electron dense carbon-carbon double bond, as I said before, and I'll keep saying this because this is there'll be times where you have to write 6-mark questions and they'll ask you, specifically things like mentioning things like electron dense compound, like these. That's why I have to emphasize them all the time. But when it's talking about polarizing it, it's talking about this bond here. Or I should just do this here. This is usually a stable bond, but because of this polarization from the carbon-carbon double bond, it's causing this to become more partially positive, and this is more partially negative as it's getting attracted. So, and that's what's making this bond a bit weaker, because it wants as soon as it does this, this bond now this bond's gonna break. It's just gonna break. There's enough energy now when this gets attracted to it for this bond to break. And now you get to this. Again, reversible reaction. So not reversible reaction. This is a reversible reaction actually. So I should probably put that down as a reversible reaction. This one in particular. Again, asymmetric compound, doesn't matter which side you put your carbocation on. I could put it on this side, I've been putting it on the other side, but it's literally the same thing here. Asymmetric compound. Sorry, symmetrical compound, not asymmetric compound. Symmetrical compound. We'll go on to asymmetrical compounds later, but that's just a symmetric compound. Symmetrical compound. Sorry, I keep saying that. It's the same on either side when you're talking about ethene. And then you have your bromine here. And here you have it. In this case here, you have 1, 2, you would have to say 1, 2 dibromo ethane. 1, 2 dibromo methane. I don't know why I did it on the top side, but it doesn't really matter anyway. 1, 2 dibromo ethane. And this one here would just be ethanol. And that's... Why is it going like that anyway? I don't even want to go back on that. You know what? You guys know what it is. That's a H there. Bromoethane. Right. So uses of electrophilic addition. Electrophilic addition reactions between alkenes and bromine, as well as alkenes and sulfuric acids, are useful. So with bromine water, bromine, this is referred to, the reaction with bromine is used as a way to identify alkenes. And so it's generally regarded as bromine water. It's the same as with Br2, but in very dilute concentrations, hence water, hence we're in bromine water. And the reaction bromine water is used to identify the alkenes. Bromine water is a light orange color, and it will be decolorized in the presence of an alkene. So if you, this question is probably the most, is always asked on the exam paper, and not directly, but they'll give you a compound. How can you determine whether or not this compound's an alkene? And say use bromine water, and it would decolorize a bromine water. So go from orange or a light orange color to colorless. Never say white is colorless, because that's what it's, same color as water. For example, colorless. Water's not white; it's colorless. But some people say white for some reason. But colorless, orange to colorless, or decolorize. The reason why this happens, this test works because bromine can act as an alkene via electrophilic addition. Is literally this reaction I've just done here. This reaction, and that's what causes it to be decolorized. And when it decolorizes, you have an alkene, because alkanes can't do that reaction. And certain other compounds that may look similar to it, like benzene, for example, can't actually do this reaction either. So this is specifically for the presence of an alkene group. So with sulfuric acid, the reaction with sulfuric acid is used to produce alcohols, and then the sulfur ion is removed by nucleophilic substitution. So the reason I say that sulfuric acid is a catalyst for alcohol production is because it's well, you have to know what a catalyst does. It's never used up in the reaction. It stays as this. It goes to it gets used, but it's not fully used up. It gets reformed again. It doesn't get shown here because I'm not going to do the whole entire mechanism of going from there to there. But essentially, this will break off, and it'll go back to this, essentially, to the sulfate ion, and then it will gain a hydrogen. It's usually from a water, because you'll have a water molecule here. Is it not from a water molecule? It's not using up water. You're forming water. My bad. But the point being, I'm not gonna go into. I'm not gonna go. The point being, I'm not gonna go through the point of going to and going through specifics. The point being that this gets reformed, and you get an alcohol. So it doesn't really. I'm not gonna go before I embarrass myself, but this sulfuric acid acts as a catalyst for that reaction, and it helps to form alcohols. So I've talked about symmetrical electrophilic addition, but it can have asymmetrical electrophilic addition. Asymmetrical alkenes can have multiple products in electrophilic addition reactions. So an asymmetric, when I mean an asymmetric alkene, propene, it's just any compound where it's not symmetrical on both sides. That's all it means. So, for example, propene. Propene is not a symmetrical compound. Let's go for. You see how it's not symmetrical on both sides? It's not. So if I was to do a reaction with hydrobromic or hydrogen bromide, it can go one of two ways, because it can form multiple reactants. It can either go via this route to form 2-bromo propane, or 2-bromo, or 1-bromo actually, propane. Yes. And so you can give to that one or that reaction. Multiples, an asymmetric alkene can give multiple products. So a reaction will favor one of the products over the other is called selectivity. As I've shown you above there with the hydrogen bromide, and the way you determine, well, in this reaction there is a major and a minor product, i.e. there's a product that's getting formed much more likely compared to the other product. And this selectivity is chosen by a carbocation intermediate. So as I've shown above the carbocation here, you get these carbocations that get formed. The reason why it's not really important when it comes to symmetrical compounds or compounds like this where it's on either side, it doesn't really matter which it's the same on either side. You get a primary carbocation on this side, the primary carbocation on this side, doesn't really matter. But it does matter when you have asymmetrical compounds, or there are other examples, but for this case, asymmetrical compounds, definitely you will get, it won't just be a primary carbocation, you get secondary, potentially even tertiary carbocations. And this selectivity is chosen by carbocation intermediate stability. So tertiary carbocations are more stable than secondary carbocations and more stable than primary carbocations. A secondary carbocation is, so a tertiary carbocation is, so you have your carbon here, one group here, R1, let's call it R2, R3. A quaternary would be that, but you wouldn't get a carbocation with a quaternary carbon. Secondary is, H here. Secondary is that, R1, R2, and then for a primary carbocation, it would just be one R group. You could just call it R to be fair. When considering which product is more, how do you determine which product is formed? When considering which product is most likely the intermediate formed, when considering which product is most likely intermediate formed must be considered. And for example, 2-bromopropane is in this case, be the most likely product because the intermediate is a secondary carbocation rather than a primary carbocation. So 2-bromopropane is most likely product because the intermediate is a secondary carbocation rather than the primary carbocation, because secondary carbocations are more stable. The reason for this being is that it has more alkyl groups pushing electron density onto the positive charge. So this is generally called the positive inductive effect. You're getting, when you have R groups, they push the electron density to this carbon atom here. So it creates a positive inductive effect. It's more stable when you get it. So when you have the more alkyl groups are pushing electron density towards the carbon, the more stable it becomes. Whereas primary carbon, when there's less alkyl groups, there's less of those. There's a weaker positive inductive effect. Both reactions will happen and you'll get both products, but one will have a major product and the other will get a minor product. And that's it. So if I was, I'm going to give you a slight example here. So if I was giving an example for, let's go for this compound here. Yeah. Shouldn't be too much of a problem. And hydrogen bromide. So first of all, I want you to carry out this reaction. I'm gonna pause the video now, carry out this reaction, and draw the structural formula for the major and the minor product of this reaction. Put major on one side and minor on the other side. And yeah, I'll explain and do that. Now, I assume you had enough time to go and do that. So this reaction, first of all, what I'm looking at is partial charges, negatively charged, from the double bond to the partial charge there, and then I'm just going to keep going down. So this would be, so this one, if you're going for the major product, it should be, the carbocation should form here, because this is a tertiary, carbocation. This is the most stable out of all of them. So this is the most likely to be, the most likely carbocation to form. So your actual hydrogen would actually form you'd form a methyl on this group. The hydrogen would be bonded to this carbon here, and then your bromide, and then you form your product. This is your major product. So your major product will be 2-bromo 2-methyl butane. Yes. 2-bromo 2-methyl butane. Now the other way that this reaction could go, this is your major product. Your major product is this. Your reaction could go another way though. Your minor product, which is also a way of being formed. You don't need to know how likely it is, like in terms of like the percentage probability. You don't need to really know that for AQA. I think there's like other examples where they ask you to do that, and like, yeah, you don't have to know that for AQA. So you have your carbocation forming here, and you'd get your bromide that's kind of acting as a nucleophile from now on. Not kind of, it is acting as a nucleophile. And then you would form your minor product, which would be 1-bromo 2-methyl butane. Yes. 1-bromo 2-methyl yes, yeah, 1-bromo 2-methyl butane, and that's it. Hopefully this video was actually useful. I waffle way too much. I'll be back here next year. I'll add.